Okay, so we're going to go through an algorithm for sketching rational functions. So the process that we've written here is essentially identical to a polynomial function. We find intercepts if we can, use first derivatives, second derivatives. Now in this case, and you'll see as we go on to it, second derivative of this function may become very difficult. So we might be able to infer concavity depending on asymptotes. So we're going to focus on asymptotes and see if we can kind of gather what we assume this function is going to look like without going into a second derivative. Okay. So we have our function here, and the very first thing we want to do is we want to look for any vertical asymptotes. Does it have vertical asymptotes to start? Yes, it does. When the bottom of this function here would be equivalent to 0, this function would be undefined. It would not exist. So we're going to set it equal to 0. So 0 is equal to x squared minus x minus 2. We're going to factor, which will give us an x minus 2 and x plus 1. We set each of those equal to 0, which means our vertical asymptotes are at x equals -1 and +2. So we have two vertical asymptotes. We also want to find out if there's any horizontal asymptotes. Now, I went through a very quick way to do this yesterday. People from yesterday, does anyone remember how we can find the horizontal asymptote very quickly here? What is it? It's 0. Okay? And we'll quickly overrule because the reason being because our function, our variable power on the top is less than our variable power on the bottom. Essentially, we'll end up with the value of 0 over some number, usually 1, which means our horizontal asymptote is 0. If you don't remember how to do that, just go watch horizontal asymptotes. Okay? So our horizontal asymptote, which would be as an equation y is equal to 0. So we already have our asymptotes for this. We're going to plot them on a graph, and we'll try to do this one step at a time. We'll get each piece of information, we'll plot as soon as we get it. Oh, wrong one, sorry. Let me get a graph out here. So let's take this graph. Okay. So we have our graph here, and we discovered that our vertical asymptotes we're at -1 and 2. Let's zoom out a little just so I can see a little bit. There we go. So at -1, we have a vertical asymptote. At 2, we have a vertical asymptote. And at y equals 0, which is our x-axis, we have a horizontal asymptote. Okay, so that's quite a bit of information to start. What we're going to do is we're going to figure out how our function acts around these asymptotes. So for our two vertical ones, let's get our line. We've set up a number line here. I'll zoom in again. Oh, that's a little much. This page is too big. Sorry. Okay, so we have our number line. Let's fix that. Our vertical asymptotes were at the value of -1 and 2. So what we want to do is work on approaching -1 from the left. Okay. So we're going to find our limit as x approaches -1 from the left. We'll find the limit as x approaches -1 from the right. So we need values extremely close to it. And we'll do the same thing with 2. The limit as x approaches 2 from the left, and the limit as x approaches 2 from the right. Okay? So we're looking to see what it's doing, whether it's trending towards positive or negative infinity. So we're going to take values that are extremely close. For -1, we'll use the value of -1.0001. Okay? And we're going to plug that in to our original equation here. Okay? And again, we're just pretty much looking for positive or negative values when we go through this. So our f at -1.0001 is equal to, when we plug that into the top of this number on top will be what? Positive or negative? Negative. Okay? So we're going to have a negative on top. And I want to keep this in factored form. That way we can keep this same idea of positives and negatives together. Okay? And this, you'll see what I mean by this. If I plug -1.001 into the first part, what do I get? A positive or negative? I'll get a negative. If I subtract those numbers, it'll be -3 something, but more importantly, it's negative. Same idea. If I plug -1.001 into here, what will we get? We'll get a very, very small negative number. Okay? And the negative, again, I told you is what's important. So now that we have this, we'll have a negative over a positive, which means what do we have? negative infinity. So we are trending towards negative infinity when we approach negative 1 from the left. So our function is doing this. Okay? It's heading towards negative infinity. We want to find the exact same idea when approaching negative 1 from the right. So we use a number that is slightly larger. Okay? We'll use f. Oh my gosh. And we'll do it in black since we did the last one in black. F at negative 0.999. Okay? Same idea. I want you guys to talk me through it. If I plug it in here, we have a negative or positive on top. Still have a negative. I plug it in here, negative or positive? Still negative. And when I plug it in here, what do we have? We'll have a positive. Okay, so we have a negative and then a negative positive. So we'll write this information down. So we have a negative over a negative times a positive. A negative times a positive is a, you guys are the best. So what are we doing when approaching it from the right? We're heading towards positive infinity. So as this approaches negative 1, this is trending towards positive infinity. Same idea with our value of 2. Take a value of 1.999 and plug it in. So f at 1.999 is equal to, I'm going to try this again by just looking at it. When I plug in, oopsie, sorry, oh gosh. Oh. It's not as accurate as you think. This takes a lot of practice. Okay. When we plug in 1.999, what do we get on top? Negative. All right, our subtraction is strong. When we plug it into here, 1.999, what do we get? A negative. And we plug in positive 1.99 here. Positive. So we have a negative on top and a negative times a positive on the bottom. So what that means, we have a negative and then a negative times a positive. What does that give us in the end? A positive. So when we approach 2 from the left, we're trending towards positive infinity. The last thing we got to test is the limit towards the right here. Okay. So let's test our limit towards the right. Just something like 2.001. Same idea. This still becomes a negative. This will become a positive, and this will become a positive. So negative divided by a positive will give us a, you're the best, there we go, negative. So we're trending towards negative infinity. So with this information, make a rough sketch here. Due to our horizontal asymptote, we know that we can't be above the horizontal asymptote and trending downwards to negative infinity. That's impossible, right? Because the horizontal asymptote is going to stop us, which means we must be below it. And then as we get towards this vertical asymptote of negative 1, we're heading towards negative infinity. Because on both sides, there's a vertical asymptote and we have a horizontal asymptote, we were trending towards positive infinity, which means we're making a U-shaped pattern here. Okay? So we know we're doing something. We don't know how low it goes, and we can get a good idea after in a second. So like we said, we don't know where it was going, and we'll figure that out by finding a Y-intercept at one point. The other information we did have was the limit approaching 2 from the right. We know it was approaching negative infinity at that point. But we haven't talked about any intercepts, so we'll get into those quickly. It's possibly one of the first things we could have done. It doesn't really technically matter the order, because we can alter our graph as we go. As you said, we need a X-intercept. So our X-intercept for this question is when our f at x would be equal to 0. So we have x minus 4 over x squared minus x minus 2, I believe. So when f at x is 0, that'll give us our X-intercept when y is 0. So we set only the top of the equation, because we only need the top of this rational function to be 0. 0 is equal to x minus 4, which gives us x is 4. So it looks like we're crossing the x-axis at a value of 4. Now there's only one X-intercept, which means we'll only cross it once. But we don't know if it's going to continue upwards in an increasing fashion, or if it's eventually going to come back down and start to decrease again. And that's where finding out the derivative will come in handy for us. So I'm going to go on this assumption that it heads back towards the asymptote. The other thing we do want to find out is the Y-intercept. The y-intercept is when our x is equal to 0, so we had f at 0 is equal to 0 minus 4 over negative 2, which gives us a value of 2. So that will help us determine how low our function really goes in the middle. Our value of 2 is over here, so now we're going to manipulate this function, and we know it's one of its lower points will go to 2. Now we don't know if that's the lowest point, but we do know it is a point it touches, so it has to go at least that low. The next step we need to do is find the derivative of this function. The derivative of this will give us critical values, so when the slopes of this function are equal to 0. So we're going to derive f at x. So f prime x is equal to the derivative of the top, is value of 1 multiplied by x squared minus x minus 2, plus x minus 4 multiplied by 2x minus 1. All over x squared minus x minus 2 squared. We're going to find out. Yeah, let's find out. So we're going to try to simplify the top here. We have x squared minus x minus 2. This will become positive 2x squared minus x minus 8x plus 4.
So there should be a minus in the top.
Where did I write the wrong?
Yeah.
Oh, yes, thank you. You're right. It is a quotient rule. So that's going to change everything we just did there to an opposite operation. So this will become negative, positive, positive, negative. So negative, positive, positive, and negative 4. I'll let you guys just double check that. We're quite good at that. So we'll simplify what we have on top. We have x squared minus 2x squared, so that's going to give us negative x squared. Those are dealt with. We have negative x plus x, cancel out, plus 8x, so we have positive 8x. And then constant terms, negative 2, negative 4 gives us negative 6. On the bottom of this equation, we still have x squared minus x minus 2 squared. Okay. We want to find when our derivative is equal to 0. That'll give us critical values. So just like before, we're just looking at the top of this equation. We need to set this equal to 0. So 0 is equal to negative x squared plus 8x minus 6. And by inspection, it looks like we won't be able to factor this. We'll have to put it into the quadratic formula. So what I'm going to do is I'm going to quickly pause and get what these critical points would be. Are we okay? So we did this off screen. So these are our values. These are points on our graph where the tangent is 0, so we have a horizontal line, so it's a critical value. Now what we want to do is find out if we're increasing or decreasing before and after these points. Okay. So the idea being that we're looking between 0.84, 7.1. So from negative infinity, we'll take the value of 0. That's usually an easy one to plug in. We'll take the value of 1 and maybe the value of 10. And we'll plug these in to find out if it's positive, negative, and positive to see what is happening at these specific points. So when we plug 0 into our, and we're looking for the derivative equation. Okay, when I plug 0 in, I end up with what looks like negative 6 over negative 2 squared, which is 4. Okay? And most importantly, I get a negative value. So because we get a negative value here, that means we'll be decreasing up until 0.84. We'll then take the value of 1. So f prime at 1 will give us 1, oops, sorry, that should be positive 1 squared plus 8 times 1 minus 6, all over 1 squared, which is 1 minus 2 squared. Could have probably done this faster, but we got 1 plus 8 minus 6, all over negative 2 squared, which is 4. And it looks like we'll have a positive value on top and a positive value on the bottom, so we'll have a positive. So because we're positive between here, we start increasing. And then finally, we'll use the value of 10. F prime at 10 is equal to negative. And this is where you guys with your lovely calculators will come in handy. 10 squared is 100 minus 10 minus 2 squared. All right, let's figure this out. 100 plus 80 minus 6 is 174. Oh, no, it's negative. Yeah, so negative 100 is 20, negative 26 over a positive value, but doesn't matter. It'll give us a negative in the end. So that is negative, therefore we're decreasing. So these points here are very important. We're going to plot them on our graph. And again, we should probably find out exactly what these critical values are by plugging them into our original equation. Our original equation at f at x was equal to, and I'm going to scroll up again just to take a look, negative x. Okay, so x minus 4 over x squared minus x minus 2. We'll plug in these values to find out what their actual coordinates are. So the first one being, and again, I'm going to get you guys to do this. I'll write them out and you guys can do it. 8,4 minus 4 over squared minus 0.84 minus 2. That'll be one of them. And the other one is f at 7.2, was it? 1 is equal to 7.1 minus 4 over 7.1 squared minus 7.1 minus 2. Anyone give me a value for the first one? A y coordinate? 1.5-ish? That's good. That's about as accurate as I'll be able to estimate. And what about for 7.1? So this coordinate here, write this in the meantime. .08, excellent. So the other coordinate being, you guys just verify if you're doing it anyways, 0.08. So these two coordinates, 7.1, 0.08, and 0.84 and 1.5. So 0.84 and 1.5, so that's important to us. 0.84 and 1.5, 0.84 and 1.5 is about here. Okay, which meaning this y-intercept was not our lowest coordinate, and I know I have a shaky hand, but I'm going to try to write this as best as we can. We know we're going to go through 2, and it looks like, from what we found, and we'll take that information. Remember, we were decreasing before this point. So we were always decreasing because we had a negative value. So let's make sense of this. This is constantly decreasing, and then essentially it comes after its asymptote continues to decrease, and then at this point it started to increase. Okay, so we start increasing there, which makes sense because after our asymptote we continue to increase. But it then has another point, another critical point. And the other critical point was at 7.1 and, what did you guys say, 0.08? Oh, did I say the last time? No, 0.08. Okay, so that's okay. So 7.1, which is around here, and 0.0 is really close to our X-intercept. So, again, I have to come through this X-intercept at 4, and I have to hit this point as being a point of where it turns around. It's a local maximum, and then it starts to come back down again. Because up to this point, we were positive, so it was increasing. And then after this point, 7.1, we got negative values, so it started decreasing. So we know that after it crosses the X-intercept, it comes up to 7.1, and then starts heading back towards the horizontal asymptote without touching it. Okay. So we've taken quite a bit of information there. And put it all together. We're going to leave out finding a second derivative because it becomes very difficult in this function, and we've drawn a relatively accurate sketch at this point. And we can imply, for the most part, our points of concavity.